Let's okay, let's see what people said. So we're looking at different probabilities of the form. The sum is exactly x. For which x value is this as large as possible? For which x value is this as large as possible? Oh, what did people say? People said 38 out of 70 people. Just around half the people said 7. Some people said 6. Some people said 12. So that's saying for which value of x is the sum exactly x as large as possible? The correct answer is 7. You said 7. Good job. So that's the maximum probability. Remember, for the sum of two dice, it's like a little pyramid. We did this one the first week. You can draw that little 6x6 probability space, right? The 36 outcomes, and the diagonals tell you the probabilities. The largest is the middle diagonal, which is 7. Okay, so if you said 6, you were off by 1, or maybe you're doing something wrong. 12 is the minimum. That's the you. So you maybe answered the question, what is the minimum value? We want the maximum value. Okay, so.
Or they've calculated, mistaken the maximum value of x with the maximum probability of x.
This is true, yeah. So another mistake maybe you made is I wanted to know what is the maximum probability. That's like, where is the maximum and what is the value? And the value was 6 over 36, which, okay. Maybe some people mix those up. I don't know why people said 12. Oh, they're doing what you said, Gary.
That's what I said,
Yeah. If you answered 12, you might have thought that's the maximum value of x, right? But I want to know what's the maximum value of the whole probability. And by the way, I don't think the answer to the maximum value of x is 12. You could easily say, what is the probability the sum is exactly 100? Makes perfect sense. You roll 2 dice. You go to the casino. You say, what is the chance that you roll the 2 dice and you get 100? Well, 0. But there's no limit on how large this lowercase x can be. 12 is the limit on the non-zero ones. But the maximum value is 6 over 36, also known as 1/6. So maybe people didn't understand the question, which is my fault for not answering and not asking it nice enough. But okay, so we're going to start with this. We're going to take this and move on to something called random variables that Gary will tell you about now, and we'll have another video about it on Friday's lecture as well.
Okay, today we're going to start with very few slides, only a very few slides, and again, I will be posting these. Mainly we're going to be working on paper today, just trying to get the idea of a random variable. So, a simple definition, a statistician's definition, and Mihai's going to give you a mathematician's approach to random variables very soon, is a random variable is a variable x is a random variable if the value it assumes corresponding to the outcome of an experiment is a chance or random event. And let's just look at some examples of. Now, why are you not moving forward? Move forward. Okay. Very odd. So typically what we'll define is we'll define some letter or some symbol as the random variable, and we use that to give our outcome a name that we want to do. So for example, you flip a fair coin twice, let x equal the number of heads obtained. Now we know when we flip a head coin twice, we could get 0 heads, 1 head, or 2 heads. And we could have labeled those in some ways, such as, an A1, an A2, or A3, or an A0, A1, A2. But this is very convenient, especially when we get into larger numbers of values of x, to just say, let x be the number of heads obtained. Consider rolling 2 fair dice. Let x equal the sum of the top faces. We have done that. That was the start of our mathematized exercise today based on that. We've worked through this before. Draw 2 balls with replacement from an urn containing 3 red and 3 white balls. Let x equal the number of red balls selected. Okay, so this experiment sounds a little different, involves urns, but from a probability perspective, well, first of all, let's consider what values x can take on. It can take on values of 0, 1, and 2, and this has got 3 reds and 3 whites. We're sampling with replacement. So probabilistically, this is the same as the very first experiment. Okay? One's flipping coins, the other's drawing a ball from an urn with replacement. But the probabilities that we're going to assign to the values of x are going to be the same in both cases, and those are going to be 1/4, 1/2, and 1/4. So we've solved those working with elementary probability before. Okay, here's another experiment. We can flip a coin a certain distinct number of times, a finite number of times, and count the number of heads obtained. Flip a coin a certain number of times. How many heads did you get when you flipped a coin, for example, 10 times? Or maybe you flipped it 100 times or 1,000 times. And you counted the number of heads you got. But there's another experiment which is possible when we're dealing with flipping a coin. And what if we said we're going to flip the coin until we get the first head? Now, if we flip the coin until we get the first head, yes, we could get it in our very first flip. But maybe we got a tail in our first flip, so then we have to go on to our second flip. And maybe we succeed on that flip, or maybe we don't. What's the maximum number of flips it's going to take us to get our first head? Got a precise number?
Infinite.
Infinite. You want to go to infinity. My goodness. Yeah, like we could keep on flipping until the cows come home. And maybe even then the cows aren't even home. You know, we don't know how many flips we're going to go. So that's a very different type of experiment than our first 3, where we had a finite number of outcomes, whereas this one, we don't have a finite number of outcomes. And going back to our urn experiment, we can look at draw 1 ball with replacement from an urn containing 3 red and 3 white balls. Let x equal the number of draws required to obtain the first red ball. Again, that experiment is identical in a probability sense with our previous one, because the probability of getting a red on the first pull is 1/2. But if we don't get a red ball, we got a white ball on the first one, well, then we have to go to a second draw. And then we can ask ourselves, what was the probability of getting the first red on the second draw? And, well, we won't calculate the probabilities right now, but we'll see this is a fairly easy one to calculate. Okay. So a couple little notes. All of these are examples of what we call discrete random variables. And the idea of a discrete random variable is that your random variable takes on either a finite number of values or what we call a countably infinite number of values. Later on, we will see another type of random variable called a continuous random variable, but for now we're sticking with discrete random variables. What do we mean by a countably infinite number of values? Well, I should leave that to the mathematician to define, but the idea is that when we flip that coin, and we have no idea how many times we might have to flip that coin to get that first head, whenever we do get the first head, we can count to that spot, okay? So maybe it's in the millions, the trillions, the whatever, the quadrazillions. It's countable to that spot. So I won't define a continuous random variable right now because we're going to just leave that.
Actually, I'm curious. Who's heard of countable infinity before? Countable versus uncountable infinity. Who's never heard of that before? Okay, great. Well,
Okay.
we'll have to give you a lesson on the Hilbert Hotel.
The Hilbert Hotel. Okay.
All right.
So, here's one thing just to note here at class. We're not going into continuous random variables yet, and that turns out to be in a different type of infinity involved. And my experience in teaching stats courses, people often have a very hard time distinguishing between countably infinite versus infinite in the sense of a continuous random variable. So that's something for the future. Okay, so just remember that at some point you're going to want to make sure you understand the difference between countably infinite and infinite in the sense of any value on a real line over some specified interval. Okay, so then we're going to define a certain type of function called the probability distribution. Or there's a reason that this, for discrete random variables, gets called the probability mass function. And the idea is that this function, this distribution, assigns probabilities for each possible value of x. When we say possible values of x, we think of it in kind of two ways. One is the values of x which will take on non-zero probabilities, but if we're being very complete in our definition and our mathematical definitions, we recognize that other values of x which don't occur with non-zero probability, they occur with probability 0. So being a good mathematician, you want to assign zeros to all those values of x which you want to assign values of x, 0 to all those values of x which don't take on the probability with a non-zero value. We'll kind of explain that a little bit better with an example, I think. So let's start off defining a random variable x for the sum when two fair dice are tossed. So again, we have worked out the probabilities on this, and if I get my dot camera working nicely, work nicely for me, dot camera. We'll start over here. Okay. So the values of x for which the sum can take on a non-zero probability is 2, 3, 4, 5, and so on up to 12. And so let's just write that down. Hey, what's going on here? Ah, okay. I know what's going on. Got it. Ah, there's my hand. Okay, got it. Okay, so we have another little convention we like to try to keep track of here, and the fact that you people are in this class means you're more mathematically inclined than many and are kind of fussy about this. So the capital X is like the name of the random variable. I.e., in this case, the sum of two fair dice. And the little x, so this is uppercase. We generally italicize it too, so that would be not a big thing, is we use the little x to designate the values. Capital X can take on. And again, for two fair dice, I guess I should have wrote the sum of two fair dice. For the sum of two fair dice, x can take on values x equals 2, 3, 4, and we don't have to fill them all in. The idea is if we can understand the pattern, we've got x takes on values of 2 to 12. So those are the values it can take on with non-zero probability. So there's various ways we can represent a probability distribution, and well, we love mathematical functions as a very general way of expressing things, but we can also express them with tables or graphs, and as long as we understand what those tables and graphs are telling us, they typically don't define the non-zero, the values of x for which probability of x is equal to 0, but it's basically understood what's going on there. So let's just take a look at this graph here. Here is what we call a probability histogram for the sum of the two dice. Okay. This was drawn in R, and we could give you the details of drawing that, but we won't bother with that right now. R has converted the probabilities to decimals, but the point is this is 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 out of 36, 6 out of 36, and then going down, and it's symmetric. And we could have done this as a table. You could go x, and so then we're going to have some function on x, and we often use p's, little p's. Sometimes you will see f's, little f's on there. And again, it's like however you define it. But let's just kind of go across here. And so x can take on values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Probability is 1 over 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, 5 over 36. And again, go back to your sheet with the dice outcomes. If you're not sure where these numbers came from, you've got to make sure you know where these numbers come from. Easy to do. And then what's the sum of your p of x over all x has to be 1. So if the sum of those probabilities isn't equal to 1, you do not have a probability distribution. If you have values in here which do not fall between 0 and 1, you do not have a probability distribution. So you've got really two conditions. Each p of x has to be between 0 and 1, and the sum of the probabilities for all values of x has to be 1. So we did that as a table. We've done it as a graph. Now I leave this as a challenge to you, and we can set this up as a mathematized problem for next day. Can you come up with a function for that, for those p of x values? Okay, come up with a single mathematical expression that for any value of x will generate p of x. Okay, it's a little bit tricky, not so bad. But we'll give it a shot next day. How we're going to mathematize it, I'm not exactly certain, but Guess we could give a few alternatives in there, something like that. Okay, so you could do an algebraic function there too. There is an algebraic function. It's kind of cool. Okay, now the other one I want to get into today is defining something called the cumulative probability function. And typically we'll use a capital F on this one. And cumulative probability function and that is defined as capital F of x equals the probability that x takes on a value less than or equal to little x. Okay, so it's looking at a cumulative thing. Now I'm going to set up some cumulative probabilities here. For our dice sum example, and so here we go. X, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so the probability x is less than or equal to 2 is simply the probability x is equal to 2. That's going to be 1 over 36.
You're just off the bottom here.
Oh, am I off the bottom? Well, that is a shame. Yes, we can't have that. Okay. So you can whip through and do the rest, but the probability x is less than or equal to 3. Well, it means x is equal to either 2 or 3, and so you go 3 out of 36. Probability x is less than or equal to 4, you're adding the 1 plus 2 plus 3, 6 out of 36. For 5, you're now going 1, 2, 3 plus 4 is 10 out of 36. And then we're going to add 5 is 15 out of 36, and then we go to the 7, add another 36, so we've got 21 out of 36, and then we're adding 5 to 26 out of 36, and then we're going to add 4, is going to take us to 30 out of 36, and then with 10, what are we doing? We're adding another 3, 33 out of 36. Hey, what just happened?
We ran out of time.
How did we do that? We didn't check the...
We didn't check the thing.
We didn't check the thing.
Let's see if we can get it back.
Eventually. Okay. While you're filling out that, we're waiting for the camera to come back. Oh my goodness, how fast that came back. That absolutely stunned me. A lot of these rooms, when they shut down, it's like 5 minutes before it'll come back. So I'm absolutely stunned. Okay, I filled in the rest of the table there. And you notice that the very last one, once we get to the last value of x that we had up in this table, we got a value of 36 over 36, which is equal to 1. By the time we get to the largest value of x, which could take on a non-zero probability, that cumulative probability has to be 1. Now what I want you to do is simply work out these numbers right here. And there's a couple of odd ones in there, yes. But could you just use this table to find f of 1, f of 5, f of 14, and f of 3.5. And you know what I didn't do? I didn't capitalize my f's. Oh, how that's shameful.
But they're capitalized. What do you mean?
Sorry, not capitalized, italicized.
Oh.
Italicized. They should be slanting a little bit. Just a little slant on them. So pretend those big F's are just slightly slanted. Slightly slanted. See, then I can fix that before I post it, right? Okay, anyhow, get those values. Get those values, take a couple minutes, shouldn't take you very long.
I think we have a subset of these in mathematized, so you're going to have to do it and then tell us what you think the answer is. Let's see. Oh, okay. I have, instead of doing f of 14, I did f of 15.
Oh, that's a harder question.
That's a harder
isn't
one.
it?
Well,
Oh, wait, maybe it's not.
too bad for you guys.
Okay.
Okay. So, and I also asked for p. P of 15 and f of 15. You work those out, along with the other ones. Actually, let's see. Let's make this one your.
Because it's cumulative probability.
That could go to the
right?
block.
So
Do you want me to
it's
change it?
just after 13 is 0.
Those numbers.
No, no.
0 after
Don't
15 is 0.
Don't.
So it's 1 plus 0 plus 0 plus 0. Taking off. Yeah, you can't get
So when
15.
this is recorded, if I walk around, recording action.
It's just like this, so
Okay, I like
So-
walking around.
you can walk around. It's
I
just
can
you
walk
won't be on
around.
camera.
I won't be on camera. Well, time does fly by quickly, doesn't it?
All right, time's almost up. Put in your answers. What are capital F and lowercase p of 15 for the 2 dice problem? All right, capital F, lowercase p. Well, I'll give you 5 more seconds for people who are still getting in. Okay. Let us see. Oh no. Okay. What did people say? Let's see. With labels hidden. Okay. Out of 70 people, 28 people picked question mark, and 14 people picked question mark. So less than half the class got it right. People are all over the place.
What's the question marks for?
Well, I made it not
Oh, that
show
can't
to
be
add some drama.
Oh, added drama.
Okay. P of 15, people think they know P of 15. Or at least half the people know P of 15. Okay, what did they say for P of 15? Ooh, 0. 0. P of 15 is 0. That's the right answer. P of 15 is 0. Okay, very good. Gary, tell us why is P of 15 0?
Because you cannot get a sum of 15 when you throw 2 fair dice.
Yeah.
Right? That is a value of x for which the probability of x is exactly equal to 0.
So P of 15 means what is the probability the 2 dice came out to 15? Like we said, if you go to the casino and you roll the 2 dice, you say, what's the chance they come out 15? 0 chance. That's what P is. So P of 15 is 0. All right, what about capital F? So capital F, people didn't know. They were all over the place. Should we let them revote, or do you want to reveal?
Oh, let's reveal.
Let's reveal. Ooh, okay, some people said it's 1. Some people said it's 0. 111 means they didn't know. These people really didn't know. Okay.
Okay.
The correct answer is 1. Ooh, this one's 1. Why is it 1?
Why is it 1?
Tell us. Gary.
Because the question is, what is the probability the sum is less than or equal to 15? Less than or equal to 15, well, in fact, all of the sums which occur with non-zero probability are less than 15. So the sum being less than or equal to 15 is a certainty, right? Right? And so, did you have anything to add to that?
The other one I was interested in, I think is cool, is what is F of 3.5? That's a cute one.
So let's go through a couple of these. F14, that was the same idea there. The probability x being less than or equal to 14, well, that covered all of our x's which occur with non-zero probability. How about f of 1? This was 0. Okay, the probability that x is less than or equal to 1. Yes, your minimum possible sum occurring with non-zero probability is 2. Now what about f of 3.5? If I asked you for p of 3.5, you would say it's impossible to get an x value of 3.5. That would be little x, the x value of 3.5, no, you can't get it. You get an integer value between 2 and 12. But what about f of 3.5? Okay, who's got an answer on that one? Who's going to volunteer an answer? Would you like to volunteer an answer?
Like for 3 is 3 out of 36, right?
3 is 3 out of 36. Yes, and is that your answer for 3.5?
Yeah.
How many said it is 3 out of 36? Everybody put your hand up. Just pretend you knew the answer, okay? Or like just claim it anyhow, okay? Because when you say what's the probability x is less than or equal to 3.5, in this case this is equivalent to saying it's the probability that x is less than or equal to 3. In other words, then we got to jump when we go to 4, but we haven't got to 4 yet, so the probability x is less than or equal to 3.5 is equivalent to saying the probability x is less than or equal to 3. Okay.
Should we draw a picture of capital F?
Pardon?
Should we draw a picture of F? The lines?
Well, actually I was going to leave this little job.
Okay.
We could do this. We could do this one. Is, again, we're going to leave you this question. This is a little tricky, optimally. Is how can the cumulative probability function be expressed as an equation? So what we want is an equation that expresses it not just for the values on this table here, but for all possible values of x, whether they are integers or non-integers. We leave that for you to solve that. Something to do over the break when you're saying, you're there, you've been like, you know, you've had your break, you've been having all this, and you're saying, but, you know, I get really bored on my break when I can't work on my probability and chance course. And therefore, I need to have something entertaining to do for the weekend. So this is something we leave you for entertainment. Okay. So I'm going to go back and do an earn thing, and we're going to keep it a little more general. Let's go back, and actually I'll put this both screens up. Here we go. So let's go back to considering an urn containing n balls of which k are red and n minus k are white. And we'll consider a couple of probability experiments where we randomly sample with replacement. Okay? And why am I working with replacement initially here? Well, remember some of the interesting characteristics when we sampled with replacement. Our probability of any particular color does not change on each pole, and the poles are independent of one another. It turns out these are both very important properties for the derivation of these distributions, and when you sample without replacement, you get into other things, other distributions. Okay, so we can look at these for deriving two special probability distributions called the binomial distribution and also the geometric distribution. And we're going to derive these distributions on paper. Why are we deriving them on paper? Because I like paper. That's all there is to it. And it's good to get in there and like mess up paper. Okay. I'm trying to get to my doc cam. Yes. Let's go doc cam on both. Doc cam on both. I draw a beautiful urn. Little K are red. And, okay, maybe I'll label them little K is red. And therefore there's N minus K, which are the other color, or what did I go with? White. So we see that there are N balls in all. Actually, I'd like to change my notation. I'm going to do a little change. From this little n, I had n balls in all. I'm going to make that a capital N, and you're going to see why in a second. Why am I going to make this a capital N? Okay. So if we wanted to find the probability of getting a red ball, it's going to be K over capital N. So this is going to be a capital N minus K. Okay, so we got a bunch of this. Now I'm going to take a random sample of N balls with replacement. Okay, and define P equals the probability of getting a red ball. And we already said that's just K over N. That's not so critical to our purposes. But we've got this value P. And I'm also going to define Q equals the probability of not getting a red ball, which is getting a white ball. Equals 1 minus P, okay? Because if you didn't get a red ball, you got a white ball, vice versa, okay? So let's just note P plus Q equals P plus 1 minus P equals 1. Okay, so you get one or the other. Okay, now, what is the probability of getting X red balls in the sample of size n. Okay? So, what we're doing is saying let X equal the number of red balls in the sample. Now, if we're, for example, we had done a sample of size 4, we could take, X can take on values of 0 to 4. So let's ask the following: let X equal the number of red balls in the sample. What values can X take on? Well, we could end up with no red balls in the sample. Or I could end up with exactly 1 red ball in the sample. I could end up with 2 red balls in the sample. Well, if I choose 2 balls, if I only choose 1 ball, I couldn't have ended up with 2, but let's kind of think it. The point is I can end up with as many red balls, because it's with replacement, as the number of balls I pull. Okay? So, what values can X take on? Here's a question that is, how many values can X take on? How many distinct values can X take on? And when we say that, we really mean with non-zero probability. How many values of X did I have in there? Give me a number. Give me an expression. How many values of X? Number of values of X. How many values of X? Oh, I gotta ask somebody. The people at the back always feel neglected because they don't get asked many questions. So, you look like you want to answer the question. How many distinct values of X? This is what you ask your friend. That's why you make sure you always sit beside smart people. Does anybody in the class? So that some days, like, you're just out of it a little bit, and like you haven't really followed it, then you pass it to your friend down there and your friend will answer. N plus 1, absolutely. How many had N plus 1? Common error, N values. Many people think N, but in fact it's N plus 1 because you've got to count the 0, right? So N plus 1. N plus 1 with numbers of ways. Okay, so just looking at my time here. N plus 1, how many X can take on? Okay, N plus 1. Okay, so how are we going to get let's derive the probability distribution. For X. Right? Derive the probability distribution for X. Okay. Oh, I'm just dying to get into this thing. Maybe I'll freeze it here for a moment so I can jump over to here. Just note, draws are independent. probability of a success, which is drawing a red here, is just this generic little p, is p, and draws are independent, and we have a finite number of draws, which is little n. So we consider, let's see, well, you know what? I've run out of time. I cannot continue this. I cannot continue this because I have run out of time before the weekend. We wish you all a fantastic long weekend. Don't spend all of the time studying. Have some fun too. And we'll see you Wednesday.
I love